All right. Well, it's 2 p.m. Let's get started. We have some people still joining, and that'll happen over the next few minutes. But I want to thank everybody for coming and attending Kianush PhD's thesis defense today. Kianush joined the the university in 2015, joined UD in 2015, um, after obtaining a Bachelor of Science in 2009 and a Master of Science in 2013 from Islamic Azad University in Mashhad, Iran, in mechanical engineering for both his bachelor's and his master's degree. He was working in airfoil aerodynamics, and for people who are familiar with that, he was actually working on some active techniques to modify drag and lift of airfoil. Then again, he joined UD in September 2015 and started working with me in January 2016. And his work has been on the airflow above surface waves. Today, he'll present some selected results from his thesis. Because of time, he doesn't have time to go over everything. But the bulk of his thesis is published in a couple journal article and a book chapter. And also he has a third paper journal article that is currently under review. So Kianush will talk for about 40 to 45 minutes. I'm going to ask you to mute your microphone while he's talking and reserve your questions for the end of the presentation. At the end of the presentation, everybody's welcome to ask a question, time at which, please unmute yourself and ask a question. And when everybody is finished asking questions, then I will ask the public to log off, and Kianush will remain here with his committee, and that is AJ Prasad, Lianping Wang, and Joe Keel from the University of Delaware, and Tetsuhara from the University of Rhode Island. And after that, so Kianush will remain with the committee, will ask question and clarification. And after that, Kianush will be excused, and the committee will stand alone and deliberate. And that's the whole procedure. So I'm going to stop sharing my screen, and then Kianush will start his presentation. Thanks.
All right. Thank you so much, Fabrice, for your kind introduction. Let me share my screen here. There we go. And here is the presentation.
Perfect.
So you can see it, right?
Yes.
Okay.
Thanks.
So thank you everyone for being here and participating in my thesis defense. Before starting the presentation, I would like first to thank my committee members, Dr. Fabrice Brown, Dr. AJ Prasad, Dr. Lianping Wang, Dr. Joseph Cole, and Dr. Tetsuhara for their continuous help and support during the course of this research. The title of my dissertation is Turbulence in the Atmospheric Wave Boundary Layer, and let's start with a brief introduction about the topic. The exchanges of momentum and energy between the atmosphere and the ocean are essential for weather patterns, sea state, and climate. So these air-sea exchanges are especially important for modeling, for climate modeling, and to predict extreme weather events like Hurricane Sandy, or even more recently, Hurricane Laura. And so they have a significant impact on very different aspects of human lives. Historically, the weather prediction models were based on engineering studies of turbulence flow over flat surfaces usually, and that basically means the total stress or the total momentum flux is parameterized using the turbulent stress. However, the surface, the surface of the ocean is not flat. So, in fact, surface waves significantly affect the air-sea exchange processes. The presence of surface waves exchanges the structure of the airflow above the interface, and that leads to partitioning the momentum flux inside the wave boundary layer. And here, by wave boundary layer in this study, we mean actually the region of flow within which the surface waves or the wavy interface influences the flow, and in our case, the flow above the surface waves. So when surface waves are appearing at the surface of the ocean, there is a complex interaction among mean flow and wave-induced flow and also turbulent flow. So in the boundary layer, in the wave boundary layer, of course, we have turbulent stress as we have over the flat plates. But here we also have wave coherent stress due to the wave-induced flow. And we also have viscous stress due to the mean flow, actually due to the mean shear. So the air-sea momentum flux is partitioned into turbulent stress, wave coherent stress or simply wave stress, and the viscous stress. So while we are here at this slide, let me point out to one point here is that, and that is the fixed measurements. Usually they cannot obtain any information below the wave crest, and the information like viscous stress and airflow separation usually is missed. So over the waves, we also have the airflow separation, and the airflow separation significantly changes the structure of the flow above the ocean waves by producing a lot of turbulence. The early laboratory studies on airflow structure near a moving surface wave were performed by Banner and Melville in 1976, and among other studies, of course. So here we focus on Banner and Melville study, and Banner and Melville investigated the occurrence of airflow separation over surface water waves. So they specifically use a smoke to visualize the airflow. They observed that over a non-breaking wave, the smoke is mainly entrained by the overlying flow, and it was attached to the surface past the wave crest. But over a breaking wave, the fluid was ejected away from the surface at about the wave crest and created an airflow separation region downwind of the wave. So overall, the earliest studies of flow structure above surface wave concluded that the airflow separation coincides with wave breaking. For the first time, later on, Raoul and co-workers in 1999 were able to obtain airflow velocity measurements over a breaking wave using the PIV technique. They observed that the boundary layer over the breaking wave separates at about wave crest and reattaches somewhere in the front of on the front slope of the next wave. So the recirculation region extends from approximately wave crest up to approximately wave trough. The resolution of the velocity measurements obtained by Raoul and et al. Was not enough actually to look at the viscous stress close to the surface. More recently, though, Veron et al. In 2007 had a high resolution measurements, and they were able to look at the viscous stress near the surface. They observed a clear evidence of airflow separation over a small wind wave. They specifically showed that the airflow separation generates an abrupt variation in the surface velocity and viscous stress, and also causes a strong turbulence and large coherent vortices on the leeward side of the waves. Overall, the airflow separation leads to a drastic reduction of near surface velocity and also the viscous stress. So the current understanding of the effects of surface waves and also airflow separation on the momentum and energy fluxes are far from being satisfactory. So we utilized a set of raw laboratory datasets obtained by Buckley and Veron 2015 to further investigate the momentum and energy balances above the surface. The experiments were performed in the Large Wind Wave Tunnel Facility at the Air-Sea Interaction Laboratory of the University of Delaware. These facilities are specifically designed for air-sea interaction studies. The tank of the facility is 42 meter long, 1 meter wide, and 1.25 meter high, of which 70 centimeters were filled with water. So the airflow velocity was obtained above the waves and in the airflow, and the PIV instrumentations were located at a fetch of 22.7 meter. So the PIV, let's talk a little bit about the PIV here. The PIV, which stands for the particle image velocimetry, is an optical method for flow visualization that uses small particles, very small particles, to seed the flow. The seeded flow is illuminated then with a light source like a laser sheet, and then imaged using a digital camera. So the motion of the particles, of small particles in the air, for example, from one snapshot to another snapshot can produce a local estimate of the velocity. So as we can see here, we have a fog generator, right? So we use fog particles in the airflow to seed the flow. So let's have a closer look at the PIV instrumentation. The velocity measurements were obtained using a combination of PIV and LIF techniques with various cameras and lasers. The water is detected within the PIV images using the LIF technique and the surface detection camera. LIF stands for laser-induced fluorescence. And in fact, we added fluorescent dye into the water to illuminate the water using the laser sheets and to accurately capture the surface. Velocity measurements were obtained using the PIV system, which is comprised of PIV cameras. There are two adjacent PIV cameras and one PIV laser. So we were able to obtain velocities within the airside viscous sublayer. The PIV laser illuminated a smaller footprint of water above the waves. We also have another laser here, which is large field of view laser, that illuminated a very large, long wave footprint of water to capture large surface profiles of the waves. So here's an example of the raw PIV and LIF images that I talked about. And we also can see the camera's field of view here. This one, the largest one, is the large field of view. And we also see the surface detection field of view. And we have the PIV field of view. The PIV images were obtained by stitching two side-by-side PIV images with nearly 7.5% overlap. So this produces a high-resolution 18.7 by 9.6 centimeter PIV image. In this image, we can also see the fog particles that were used to seed the airflow. So here is the resulting horizontal velocity estimate. We have one velocity vector for every 188 micrometer squared. And on average, there are about 985 by 255 velocity vectors in each PIV image. Also, the PIV velocities were obtained at a rate of 7.2 hertz, which that means like 7.2 velocity estimates per second. Okay, here we show again the same PIV image, but now we plot it above the large field of view surface where we can see multiple wavelengths. So let's talk about the experimental conditions that we have. The experiments were performed for different wind speeds. So that the wind speed, the U10 wind speed, that means like the 10-meter extrapolated wind speed, varying from 0.89 meter per second up to 16.59 meter per second. And that is corresponding to wind waves with a slope of 0.07 up to 0.27. By using the large surface profile, we are able to decompose every PIV water surface into its spatial Fourier components, and from there design a following wave coordinate system that follows the wave shape close to the surface and tends to be rectangular, a rectangular coordinate system, like a Cartesian coordinate system, far away from the surface. So such a coordinate system actually allowed us to calculate the velocity profiles, the mean velocity profiles, even below the wave crest. We also can obtain some phase information using the Hilbert transformation of the surface profiles. So we actually were able to determine the phase of each velocity profile, right? Like here, we know exactly the phase of this velocity profile and this velocity profile, and from there to calculate a phase average velocity. So we decompose each instantaneous velocity field to a phase average velocity field and a residual that is the turbulent velocity. The phase average velocity can be further decomposed into mean profiles, the mean velocity, and wave-induced velocity. So this leads us to an instantaneous decomposition in decomposition of the instantaneous velocity into a triple decomposition of mean velocity, wave velocity, and turbulent velocity. So to put the phase averaging process into perspective, let's have an example of how we do the phase averaging procedure. We are getting from the instantaneous velocity field to the phase average velocity by putting together all the profiles at phase 0 here, for example, and then ensemble average them together. So we would have an ensemble velocity profile for phase 0. We can do the same thing for the phase pi, putting all the profiles together and then ensemble average them together. We would have an ensemble average velocity profile for phase pi. So if we do the same thing for all the phases that we have, we end up with a phase average velocity field like this. So for each phase average field that we have, there are 144 phase beans, which means like each bean is 2.5 degrees, and more than 31,000 profiles goes to each bean. So also, if we average over all the phases that we have, we can obtain an ensemble average profile. So now that we have the mean velocity and the phase average velocity, we can obtain the wave-induced velocity. In fact, the wave velocity, U tilde, is obtained by subtracting the mean profile from the phase average velocity. So that would be our U tilde. Here, the deviation from the mean flow, for example, deviation on the windward side and the leeward side, shows an acceleration on the windward side of the wave and a deceleration on the leeward side of the wave. So here is an example of the triple decomposition that we talk about for different wind speeds, like all the wind speeds that we have in the current experiments. The first column shows the instantaneous velocity fields, which are decomposed to mean profiles and wave-induced velocities and also turbulent velocities. So here we have also to mention that this triple decomposition actually allows us to directly obtain turbulent stress from turbulent velocities wave stress from wave velocities, and also viscous stress from the mean profiles or mean shear. So next, let's look at the flow structure in the current experiment. And first, we present the mean flow structure. So here we see the mean velocity profile for the flat water surface, like there is no wave is generated at the surface. And we show that in the wall layer coordinates. Here, U plus is the average velocity scaled by the friction velocity, and zeta plus is the height scaled by U star and nu. The mean velocity profile above the smooth water surface follows the classical turbulent boundary layer log law very closely. And in that, like we can clearly see the viscous sublayer very close to the surface, and also the buffer layer or the transition layer at about zeta plus 10. And further away from the surface, we can see the logarithmic layer. But when waves are formed at the surface, we can see that the mean profile, the mean velocity profiles start to deviate significantly from the law of the wall. So next, let's look at the phase average flow. Here, we show the phase average horizontal velocity at a frame of reference moving with the waves. And that means we subtracted the phase speed of waves from the phase average velocity. So below the critical layer, and by the critical layer, the critical layer is defined as a height at which the airflow velocity equals the phase speed. So below the critical layer, airflow is moving in a direction opposite to the main flow, as you can see here, right? And above the critical layer, the airflow travels in a direction of the main flow. So this is clear from two low wind speed cases, and we can also see that from higher wind speed cases that we have if we plot them in a logarithmic vertical scale, and that is because the critical layer for high wind speeds are very close to the surface. So generally, the critical layer follows the wave shape very closely, but it has a smaller amplitude. So in the second column here, we also show the horizontal velocities, but with the mean velocity subtracted. So in fact, these are our U tilde. These are the wave coherent velocities. So the horizontal velocity, the horizontal wave velocity, whether to say, is positive along the windward side of the waves, and it is negative along the leeward side. So again, we already mentioned this, right? This indicates that the acceleration, like this indicates the airflow accelerates and decelerates as it passes the wave crest. And finally, we can see that the wave velocities in general become more intense as wind speed increases. So now let's move on to the next part, which is like, let's look at some momentum flux results, some momentum flux measurements. Okay, so excuse me. In the current study, we are using an orthogonal wave following coordinate system that I already showed how the coordinate system works, and we fully transformed the decomposed governing equations into such a coordinate system. So that is in fact allowing us to investigate the surface parallel momentum and energy balances. Here is the mean momentum equation for a two-dimensional flow over wind waves. So I'm not going to the details of derivation of this equation, but here we use a boundary layer scaling in which we assume that the wave amplitude is small compared to the wave length. And further, we neglected all the terms of order of magnitude ak squared and higher. So here we especially focus on three main components of the mean momentum flux, and they are turbulent stress and wave stress and also viscous stress. So let's look at them one by one. First, we show the phase average distributions of turbulent stress. So here, the phase average turbulent stress is shown on linear and logarithmic vertical scales. Here, we normalize the turbulent stress using the total flux. So the turbulent stress shows a phase-locked behavior, and it in fact shows a peak at about the middle of the leeward side of the waves and a dip just upwind of the wave crest. So the turbulent stress is also significantly reduced within the viscous sublayer, and that is true in all experimental cases. So we can see that in a logarithmic scale, vertical scales for higher wind speeds. The turbulent stress also close to the surface shows a pattern of a long wave asymmetry. And that means it is intense and positive downwind of the wave and a slightly less intense and positive upwind of the waves. We also observe that the maximum of turbulent stress is always located downwind of the waves. And we think that is because of the airflow separation. But let's see how that is happening instantaneously. Here, we have a non-separating wave, right? The top panel shows the instantaneous airflow velocity, and the bottom panel shows instantaneous U prime W prime. On the right, we have the same thing, but over a separating wave. The top is the instantaneous velocity, and the bottom is the instantaneous U prime W prime. So this wave is at the same exact wind speed, but it just experienced airflow separation. So instantaneously, the long wave distribution of turbulent stress varies over separated and non-separated waves. The turbulent stress is extremely intense on the leeward side of separating waves, where we can see there are some coherent structures. And in fact, that is happening in the region of airflow separation. This partially explains the increased or enhanced turbulent stress downwind of the waves in the phase average fields that we saw. So next, we look at the mean profiles, the ensemble average profiles of the turbulent stress. So here again, we normalize the turbulent stress using the total flux and the height scaled with the wave number of the dominant wave, Kp. So the contribution of the turbulent stress to the total momentum flux increases with wind speed. The turbulent stress also is significant part of the total wind stress away from the surface. And very close to the surface within the viscous sublayer, turbulent stress approaches zero. The turbulent stress also reaches the total stress at a height about Kp zeta 0.5 for all wind speeds. Also, we can see that the turbulent stress is reduced close to the surface, and that is mainly because of the wave stress. So let's look at the wave stress then. Here's the phase average wave stress, and again we show in a linear and logarithmic vertical scale. So overall, the wave-induced stress is intense near the surface in all cases that we have. For all wind speeds, the wave stress shows an long wave asymmetry in that positive intensity of wave stress is asymmetric. And those asymmetric pattern is located at or above the critical layer. In fact, the wave stress is slightly intense on the leeward side of the waves. So these regions of positive wave stress are intertwined with negative wave stresses just above the wave crest and downwind side of the wave trough. We note here that the positive wave stress represents momentum transport toward the water surface, so that would be a downward flux, and a negative wave stress indicates an upward momentum flux, right? That would be an upward flux. So here we're gonna look at the ensemble average wave stress. So looking at the mean profiles of the wave stress, we see that in general, the wave stress decreases to a negative extremum from an almost zero value far away from the surface, and it then increases rapidly to a large positive peak close to the surface. So most of the wave stress is produced near the surface. For example, in the case of U10 9.57 meter per second, the wave stress is about it's about 45% of the total stress at a height of kp zeta 0.02. So this high contribution, in fact, reduces over all their waves. And for the lowest wind speed here, wind speed of 2.25 meter per second, the wave stress is about 25% at a height of kp zeta 0.1. So next is the viscous stress. Here are phase average viscous stresses in a linear and logarithmic scale. So the phase average distributions of viscous stress present an asymmetric pattern close to the surface, and so those are actually can be better seen from the logarithmic scales here. The viscous stress is intense upwind of the waves with its maximum value about the wave crest, and less intense downwind of the wave crest with its minimum in the middle of the leeward side of the waves. With increasing wind speed, these peak values of the normalized viscous stress reduces and shifts downstream. So far from the surface, however, like you can see it here, far from the surface, the viscous stress rapidly drops to zero, and there the effects of viscosity become negligible. For the lowest wind speed, we observe an enhanced viscous stress near the surface for almost entire upwind side of the wave. And then that means by enhanced, we mean that like the viscous stress is slightly greater than the total flux. So let's look at our instantaneous fields one more time. Here we can see the instantaneous velocity field with its corresponding surface viscous stress over a non-separating wave. Okay, and the same thing for the separating wave. Over the non-separating wave, the viscous stress or the surface viscous stress is positive everywhere, right? And it is, in fact, a significant portion of the total flux. But over separating wind waves, the airflow separation causes a significant drop in the surface viscous stress at the point of separation. The viscous stress, the surface viscous stress, then becomes negative in the recirculation region and remains approximately zero below the separation region. This explains the reduction of phase average viscous stress downwind of the wave. And also here we can also see that the viscous stress is slightly enhanced just before the wave crest over the separating wind waves. So let's finally look at the mean profiles of the viscous stress. Overall, the viscous stress contribution to the total flux decreases with increasing wind speed. For the lowest wind speed, of 2.25 meter per second, in fact, the viscous stress supports more than 80% of the total flux at the surface. And this large contribution remains significant up to a dimensionless height of about zeta plus 20, with about 30% contribution to the wind stress. So the viscous stress remains significant for moderate wind speed. Here, for the wind speed of 5 meter per second, Newton 5, we can see that the viscous stress is about 55% of the total stress. And it is about 35% of total stress for wind speed of 9.57 meter per second. So now let's turn our attention to the kinetic energy budget, right? We've looked so far at the partitioning of momentum flux and its three major components, the turbulent stress, the wave stress, and the viscous stress. So we can also decompose the kinetic energy equation and look at the interaction among mean, wave, and turbulent kinetic energies. So the kinetic energy budget equation for the mean, wave, and turbulent flows in an orthogonal curvilinear coordinate system can be expressed by these equations. So here the first equation is the mean kinetic energy, the second one is the wave kinetic energy, and the last one is the turbulent kinetic energy. Let's look at some of the terms here. And for the mean kinetic energy equation, we have this large transport term, which is showing like the transport of mean kinetic energy. The second term is the dissipation. The third term, PW, is the wave production, and that is appearing in the wave kinetic energy equation as well. The last term is the turbulent production, PT, which is also appearing in the turbulent kinetic energy. The second equation, the wave kinetic energy equation, we again have a large transport term showing the wave kinetic energy, and the second term is the dissipation. The third term is the wave production, PW, and there is the new term, the last term here is a new term, which we call it wave turbulence interaction, and that is going to be appearing in the TK equation as well. So the last equation is the turbulent kinetic energy. And here we see that we again have a large transport term showing the transport of the TKE dissipation, and the PT, the turbulent transport, and again, the wave turbulence interaction. So in summary, the mean, wave, and turbulent kinetic energy equation can be presented as this set of equations. So as we can see, PT, PW, and WT show the interaction among mean, wave, and turbulent fields. And in fact, turbulent production, wave production, and wave turbulence interaction terms produce wave and turbulent kinetic energies and transfer the energy between the waves and turbulence. So therefore, we are gonna focus on these budget terms mainly. Here, we estimated the PT, PW, and WT, again, using the boundary layer assumptions. And again, we neglected all the terms of the order of magnitude of AK squared and greater. So let's start with the TKE production. The turbulent production is positive at all heights above the surface, and that means the energy is transferred from the mean flow to the turbulence. Overall, turbulent production is concentrated close to the surface, below Kp zeta, approximately 0.2. Away from the surface, turbulent production approaches zero, and that is because of the small magnitudes of mean velocity gradients. Very close to the surface, and within the viscous sublayer, the turbulent production quickly drops to zero, and that is because, in fact, turbulent stress is significantly reduced within the viscous sublayer. The peak turbulent productions that we see here, close to the surface, are attributed to high shear layers and a strong turbulent stress in this region. In fact, the airflow separation largely contributes to turbulent production by generating a strong and intense turbulence in the lee side of the wave. So here we show the PT, the turbulent production, against the Kp zeta. But the relevant vertical scale for the PT is likely to be the viscous sublayer. So it is quite useful to plot the production term in one layer coordinates and compare our results with the classical turbulent flow over flat plates. So here we show classical experimental results over the flat plates and also some of the DNS results. So we see that here, first of all, like PT is normalized here by the wall variables, the U star and nu. So we have PT plus here. So over the smooth water surface, the PT plus closely follows the classical turbulent boundary layer flow over flat plates. But when waves are appearing at the surface, turbulent production starts to deviate from the law of the wall. In fact, with increasing wind speed, the profiles of turbulent production are reduced compared to the law of the wall close to the surface, in like zeta plus smaller than 30. This is mainly because the mean shear flow also contributes to generating surface waves, and such a contribution, in fact, increases with wind speed. So next, we're going to look at the wave production. The wave production indicates the energy exchanges between the mean and the wave coherent flow. In general, near the surface, the wave production is positive, and that shows the transfer of energy from the mean flow to the wave perturbation field. Farther above the surface, however, between Kp zeta of about 0.1 and 0.4, wave production is negative, and energy is transferred from the wave field to the mean flow. Farther away from the surface and outside the wave boundary layer, the wave production quickly drops to an almost zero value, which is somehow expected. So here we note that, in fact, the variations of wave stress and wave production are quite consistent, since the mean shear is positive at all heights in the current experiments. The wave stress, right, we saw this figure previously. The wave stress is positive close to the surface, and it then reduces rapidly to a large negative values farther above the surface. And that is basically what's happening in the wave production term as well. It's positive close to the surface, and it goes to a slightly negative values. So here, the large negative values of wave stress, right, that we see here, are abated by the mean shear, and that's why the production has very slight negative values. So here again, we showed the wave production term against the Kp zeta, the dimensionless height Kp zeta. But the relevant vertical scale for the PW, the wave production, is likely to be the Stokes layer height. And the Stokes layer height, delta here, is defined as the square root of 2 nu over omega. And that is basically a diffusion length scale based on an oscillatory boundary layer. The Stokes layer height provides a reasonable collapse of the location of maximum wave production, which is located slightly below the Stokes layer height at zeta over delta equals 1. Above the Stokes layer height, the wave production exponentially decays and it goes towards a zero value. So finally, we are presenting the wave turbulence interaction term. The wave turbulence interaction term, WT, shows energy exchanges between the wave and turbulent fields. And we observed a drastic vacillation in the rate of turbulence and energy transfer with the height above the surface. In fact, away from the surface, WT is approximately zero. And that means that there's no interaction between wave and turbulence. WT is generally increases to a positive peak from an almost zero value, right? To a positive peak near the surface, and that means the energy is transferred from the wave to the turbulent field. There is also a very thin region close to the surface wherein WT is negative, and the energy is transferred from the turbulence to the field. But this region is very thin, and it's literally negligible. So far we showed the turbulent production, the wave production, and the wave turbulence interaction terms, the WT. So in addition to these budget terms that we showed, we can also complete the balance of the kinetic energy equations. I probably do not have time to go through all the kinetic energy equations budgets, right? But we can do, for example, one budget. Let's do it like for the wave kinetic energy that we have the best estimates here. So here is the wave kinetic energy budget as we've seen it previously. So here in this equation, we can neglect the local time rates of wave kinetic energy. And that's because, first of all, our measurements are statistically yesterday. And secondly, other measurements, other field measurements also suggest that this term is very small and negligible. There's one term in this large transport term that we cannot directly measure, and that is the pressure transport. So let's rearrange this equation and isolate pressure transport term on the right-hand side of the equation. Okay, there we go. Now the pressure transport can be obtained as a residual in this equation. So here, the first term is what we call it the total transport term, which is the sum of the wave and the turbulent transport terms. The second term is the wave-induced viscous diffusion, where all viscous effects are considered in this term. The third and fourth term here are familiar. So this is the wave production, and this is the wave turbulence interaction term, and the TPW here is the pressure term. So we come up with a budget for WKE for the wave kinetic energy equation like this. Now we can look at all the terms in this equation for different wind speeds that we have. Here, the wave production is indicated by solid black lines, and the pressure transport term is shown by solid gray lines. The wave turbulence interaction is dashed lines, total transport is dashed dotted lines, and the viscous diffusion is dotted lines. So we observe that the wave production and the pressure transport terms dominate close to the surface for all experimental conditions that we have. Wave production is the principal gain term, and the pressure transport is the primary loss term here. The wave turbulence interaction term is smaller than both wave production and pressure transport terms, but it is not negligible around Kp zeta 0.1. And finally, the viscous effects are negligible at all heights for all the experiments. So with that, I can wrap up with the conclusions of the work. So today, we showed high resolution velocity measurements in the airflow above wind waves. The velocity measurements were obtained within the viscous sublayer using a combination of PIV and LIF techniques. They also decomposed the flow into mean, wave, and turbulent components and further investigated the corresponding mean, wave, and turbulence momentum and energy budgets. So first of all, we saw that the presence of surface waves leads to a wave phase coherent variation in the wave boundary layer. The phase average turbulence stress is positive everywhere above the waves, above the wind waves, and shows a clear influence of airflow separation downwind of the waves for all experimental conditions. Also, away from the surface, the turbulent stress is a significant portion of the total flux, while closer to the surface and within the viscous sublayer, the turbulent stress approaches zero. For the wave-induced stress, we observe that the wave stress changes sign along the wave. It shows a downwind. It shows a downward momentum transport close to the surface, and an upward momentum transfer farther above the surface. Also, most of wave stress is produced near the surface. So the viscous stress is at its highest on the windward side of wave, and its minimum occurs in the middle of the leeward side of the wave. We also found that the contribution of viscous stress to the total momentum flux is not negligible for low to moderate wind speeds. And it is more than 80% of the total stress for U10 2.25, and it is about 35% for U10 of 9.57 meter per second. We also look at the wave turbulent kinetic wave and turbulent kinetic energy budgets. Over wind waves, turbulent production is positive at all heights, with a peak near the interface, and that means the energy is transferred from the mean shear to the turbulence. Also, away from the surface, the turbulent production approaches zero, and the wave production also, like there's a similar, the wave production is also positive near the surface, right? That is kind of similar to the production, but away from the surface, the wave production becomes slightly negative and energy is transferred from the wave perturbation to the mean flow. Finally, we found the viscous sublayer and the Stokes layer height as natural vertical scales for the TKE and WKE production terms. And with that, I thank you your attention, and I'll take any questions. Thank you so much.
Thank you, Kinush.
So,
all right. Well, here we go.
okay.
Now is time when people can ask questions. Maybe I'll ask the committee to hold their question for the private session, unless you think you have a question that needs to be asked in public. All right. Anybody who wants to ask a question? I know those Zoom things are
weird thing.
Awkward.
It is actually.
I can ask a question.
Tobias, please.
Yeah. Well, first, really nice work and a great presentation. Thanks a lot.
Thank you.
How do you use those nice results for practical improvements of wind stress estimates? I guess that's something you mentioned in the introduction, right? That's something you're after.
Yeah. That's actually a very great question. So one thing that we've tried with doing these kind of experiments that can help the parameterization of the probably numerical models is that if we can provide some wind stress information to numerical models. For example, we did that one with Tetsu, and we provided some roughness length scale, roughness at the surface for the LES model. So the one thing better than roughness would be like the distribution of wind stress at the surface, if it can be provided for the LES numerical models. That would be a perfect parameterization, I guess.
Thank you.
So, sure.
I also have a quick question. So I like the scaling of the production with the Stokes layer, but I wonder if for the high wind speed, so it seemed that the viscous stress is a small proportion of the total, so part of the stress will come from pressure forces. And I wonder if then there should be also some displacement, in flow over urban canopies we will call a displacement height, that might have an impact there on top. I'm not sure what the Stokes layer entails, but it sounds to me like it's a purely viscous length scale.
Yes,
and so
right.
if when the viscous stress becomes a small percentage of the total, then I would imagine there will need to be some geometry, wave-related length scale also in the recipe. Perhaps that I don't know if it could help.
Yep, that is actually a very good point, and we tried several different scales, and we tried to include the wave shape, the AK influence in the scaling. Like we didn't get a very physical intuitive kind of scaling, we could make the profiles to collapse better for the production. For example, using inserting the AK, the wave slope into the scaling, but we couldn't get exact physical interpretation for that, and that is 100% right. That needs to be further looked into and find the exact situation for that. And I think that would be some relation between like the highest wave slope, for example, that we have before the breaking, and the wave slope for each wind speed that we have. So that should be a relationship between these two.
Okay, well, thanks, and fantastic presentation. Great work.
Thank you, Marco.
Do we have any other questions?
I have one, if I may. Mark here.
Sure.
Go ahead.
Actually, 1.5 questions. First of all, very nice presentation. Excellent work. Very, very high quality analysis. So thanks for that. My first question was actually similar to Tobias's, but more specifically, how does the partitioning, how does studying or estimating the partitioning of momentum flux and energy or TKE budgets help for the atmosphere ocean interaction problem, for the sea state prediction, for the weather prediction, and so on and so forth? So specifically the partitioning, how does that contribute, or can it contribute? And then the half question was about the critical layer height. You mentioned that there's the flow is in the opposite direction to the mean flow, or to the flow away from the surface at the critical height. What does that mean? Does that mean there's shear at the critical height or vorticity?
Good questions, actually. So about the first one, I think if we have a clear or better kind of understanding about the partitioning, we can directly use that information for the parameterization. So we can, if we know in what kind of regime the turbulent distress, or at what height the turbulent distress dominates, so we can use the turbulent distress only to parameterize. And for example, we showed that viscous stress is going to be an important part of the partitioning for the like moderate wind speed. So this information can be directly used. And for the critical layer height, I'm not sure actually if that is a shear over there, but like there's definitely a region that waves are influencing the airflow above the surface more. Like that would be the region that we expect that the waves are going to influence the airflow above the surface up to that height. So I'm not sure if there is, like, we usually see in some flow patterns, we usually see a phase kind of movement, like there is a shift in the pattern that we see. For example, the wave stress, I guess that would be a good example. For example, the wave stress here, like you see, there's positive, negative, not this one actually. Let me see if I can get to that. Finally, yeah. So yeah, so there are some shifts in the at the critical layer height. So I don't know if that shift in the pattern of the flow is related to a shear existing over there or not. But yeah, that's a great question. I have to look at that further actually. Thank you, Mark. I don't know if that answers your question.
Yes, thank you.
Sure.
Could I ask a question, please?
Please, Pablo.
Sure. Hey, Pablo.
Hi, Kian. It's a super presentation, echoing Mark, a wonderfully sophisticated analysis. just a broad general question. Your perspective is very two-dimensional.
Mm-hmm.
Is there circumstances where that might begin to be a bad approximation? Perhaps not.
Yeah, perhaps like for like yeah, we had a hard time actually for the turbulent budgets. Like that's a 3D phenomenon, right? Turbulence is 3D. So that's right. We didn't have any information for the turbulent flow in the lateral direction. So that was a problem when we wanted to estimate, for example, the production. Production has 9 terms. So we are able to only measure like 6 or 5 terms, right? Independent 5 terms. So we had to use some assumptions. For example, for the lateral turbulent stress, we just used an assumption that the turbulence in the lateral direction is an average of the turbulence in the eastern-wise direction and in the vertical direction. So there are some studies showing that this is a good assumption, but definitely we need some information about our lateral direction to be 100% sure about that. But based on the field measurements, I think that would be a good assumption, but that would be the place we need the 3D dimensional measurements.
That's a wonderful answer.
Thank you.
Do we have other questions for Kinush? From
I just have a quick question. So did you just tweak the wind speed, or did you also consider changing the water flow speed? And what was the water flow regime in your experiments? Like, were you considering the laminar flow, or the water flow was also turbulent?
I guess that the water flow was definitely turbulent, but we didn't consider the water side. So we just look at the air side and the airflow above the surface waves. So, but the water side is turbulent, but it's not. We didn't look at that.
Okay, thanks. How would you estimate that the water side can affect your story overall?
So yeah, definitely that's probably the continuing of this project. So we are going to measure at the same time the flow above the surface and below the surface. So that would be the future of this work actually.
Thank you. Excellent
Sure.
work. Thanks.
Sure, thank you.
last few questions, if we have them. Okay, well, if not, I want to thank you again, everybody, for attending Kinush. This is Defense, and I'm going to invite everybody except committee and Kinush to log off. And thanks again. Have a good day.
Thank you.